Until what time do I actually have? Is it like 45 minutes or is it?
40 minutes.
Did you say that you will show the so it's 40 minutes. Okay. Is it already 10? So a quick reminder, there's a whiteboard in the hall. Please propose your lightning talks, even if you submitted them online already, and vote for them. And Lennart Poettering will tell us about the bus.
Okay, can you hear me? I'm a bit sick. I got a cold, so my voice is a bit in ruins, but I hope it will work out good enough for the duration of this talk at least. I think last year at this very conference we spoke a little bit about kdbus. kdbus is something that hopefully will, it's really done. It's like it has been turning a couple of circles on LKML, but it's really going to be finished hopefully in the default kernel of the distributions very soon. So I would like to take the opportunity this time to actually give an overview why this all matters, and with one point of view, like focus specifically, which is we noticed that a lot of the basic building blocks of the OS, like the low-level system services that we have, still roll their own IPC stuff. at the moment. Like you see that yeah, if you have storage subsystems or any other kind of subsystem of the lower levels of our stack, you realize that they still try to like think that dbus is a bad thing or something, roll their own IPC, even though, well, the thing is, it's really, really hard being better than dbus. And in this talk, I really would like to shed some light on why specifically that is. So the message of this talk is really supposed to be, don't roll your own IPC. Dbus is better. It's better performance-wise. It's better functionality-wise. It's better portability-wise. And if you still do your own thing, and your own thing could be like you use FIFOs or sockets and things like that, yeah, you cannot beat it. Don't reinvent the wheel. I mean, of course, we in the Systemd project reinvent the wheels from time to time too, but it's really, this one is not one you can win specifically if your focus in your project is not being an IPC system on your own, right? You should not make this mistake assuming that if you actually want to develop some storage service or whatever, or some other service of the system service, that as a side project you can write a better IPC than dbus. That's really, really hard to do. If you want to be a better IPC than dbus, you probably have to make that your main project. Anyway, so if you hack a system daemon and you provide a client tool to it, it's already IPC. I mean, people should not underestimate that. So dbus should not be that afterthought that you add on top of what you already have. And for all the stuff that you internally have, you talk some other kind of IPC. IPC really means inter-process communication, and regardless if it's tiny or whatever, dbus is the best answer for it. So let's discuss a little bit like why precisely it is so much better. So the first thing is discoverability. Discoverability is pretty simple. It's just about the possibility to enumerate the services, IPC services that are actually available on the system. That's very easy with a dbus. It is usually not available with any kind of other dedicated IPC system, and specifically it's not available if you roll your own via AF Unix sockets or something like that. Pretty close to that is introspection, right? It's one step further after you figured out that these services are viable. With introspection, you can actually figure out what precisely those services offer. The objects, the interfaces, and things like that. We'll come to that a little bit later. So this is amazing. Like, you should not underestimate that. It's not only useful for developers, because they can actually look at their system and figure out where APIs might be available that might be useful, but it's also great for administrators because they actually can figure out what's actually going on. The entire system is not as opaque as it could be if they have no understanding about the IPC systems that are actually going on. We'll later in this talk we'll have hopefully a bit of a demo how I'll show you how to make use of these kind of discoverabilities, because I mean dbus in a way it introduces a number of concepts that might be off-putting to administrators in a way because they're new concepts and they're not used to them. It's actually not that difficult, all of that. And I think the win by making these things discoverable and introspectable is immense. Access control, right? Like if you build your own IPC, you have to deal with the problem of access control. Only privileged staff should be able to access privileged operations, and only unprivileged, So you basically need to always check for all the operations that happen if the client is actually allowed to do that. dbus has an elaborate scheme for access control in place, right? You have per service access control, you have per method access control, and through the policy kit hookup, you actually have interactive access control, where interactive access control means that if somebody wants to write an interactive client to your stuff that runs locally, you can even ask security questions interactively, so that there's a nice, like in GNOME Shell or something, a nice authentication box popped up and ask for your password again before you're allowed to do something. So like this kind of hookup even, the fact that it's integrated in GNOME Shell and KDE and these kind of things for the authentication is something, if you ever wanted to do that on your own IPC, in your own IPC, you would have to sit down and write a lot of code and get it included into a lot of projects. then this one is a pretty important one. Universal programming language support. If you use dbus, you can be sure, regardless which programming language you pick, if it's C, if it's PHP, if it's Perl, if it's Python, it doesn't matter. There's going to be a pre-existing binding for it. So you don't have to spend your time writing bindings for the many, many languages that you have. It's already done for you. Like, this is not to mean that all the bindings are equally good. They aren't. But this is kind of like, yeah, if you use dbus, you can forget the entire question about what people should run on the client side because it's already going to be there. It has a powerful debugging toolbox. Like I already talked a bit about the discoverability and introspection, which is already a pretty useful debugging tool because you can figure out what's actually viable in the system. But it goes further. We have powerful monitoring and eavesdropping tools. So you can actually, if you do networking, you know how wonderful Wireshark is, right? Like because it allows you to trace down what's actually happening on your network. All these tools are also viable for dbus, right? Like we have commands how you can figure out, like get a dump of the messages being exchanged on the system for IPC. And that is incredibly useful. Like you can like get for every interaction that's on the system that is between two system services, you as an administrator or you as a developer, you can just ask what's going on there. You can plug in your monitor and get the stream of stuff out there. That alone, I mean, this debuggability that's even available for administrators is such a major benefit over any kind of self-written IPC system. Then there's a whole story about kdbus. I mean, this talk in general is not specifically about kdbus. This is about all of dbus, the dbus that is 10 years old, that has been established on the desktop firmly and in other areas as well, like the one that your Unix system speaks and everything else. But kdbus is just one facet of it. It's kind of the new iteration of local IPC, like that if you use dbus on Linux, how it accelerates things and how it extends some functionality. kdbus, as mentioned, I talked about that pretty much 1 year ago, gives way better performance. It's fast enough that you can actually use it to exchange not only control messages, how classic dbus was designed for, but massive amounts of data in a very efficient way. It's also portable, though with certain limits. Portable means that, there's dbus, like the official dbus runs on Windows even, on macOS and all the weird operating systems. The mostly, though, I put there because if you use kdbus, then you get dbus plus a couple of additional features. If you use those features, like for example, if you rely on the fact that huge data transfers are ridiculously fast in kdbus, then of course you lose that portability because other operating systems will not provide that. But I think it's a fair deal. It basically means, yeah, if you use it on Linux, if you use it with kdbus, everything's ridiculously awesome. But it still works mostly nicely on other operating systems too, because dbus is viable pretty universally. Type safety, it's the next one. Like if people roll their own IPC systems, they usually start by putting together their C structs, and then they put stuff in there, and it's completely type unsafe. The messages have no idea what they're actually carrying. They're just carrying binary blobs. With dbus, you have type safety for the entire thing, right? The vocabulary of types is extremely rich. It's not this thing that was an afterthought. It's actually something that was built into it right from the beginning. It has, the obvious things are structs and things like that, and just integer types and strings. It has all that. It also has variants, which is incredibly useful. Like variants being this thing where you don't specify in advance the type, but allow the type to be part of the value. It has dictionaries and a couple of other things. What is specifically interesting is like in the newer dbus versions, and specifically when you run kdbus, but probably even also soon if you do not run kdbus, is because it uses this marshalling that was developed by the GNOME project, gvariant, you actually get O of one axis. What does that mean? Many of you probably studied computer science, so you know the O notation. The background of this is basically if with that type system that dbus uses now, you encode an array of strings, like of a variable length strings. Then traditionally you have the problem that if those strings have variable sizes, to get to the 505th string in your array, you traditionally would have to go through the 504 strings that came before it to actually find the fifth one, because you don't know the length and you cannot jump to it. Now with Gvariant and this kind of marshalling that we have now, all of that is encoded in a really, really nice way. I mean, I can always encourage everybody to have a look at Gvariant encoding. It's one of the best designed marshallings I've ever seen, and that's why we adopted it for dbus. It gives you O of 1 access for all the data access. Like if you have an array with variable sizes in it, it doesn't matter. You can jump to any element in those arrays in a very, very space-efficient way in O of n time. That might sound like uninteresting, but it's really, really awesome, because it basically allows you to not demarshal the messages you, I'm not sure if you guys know the concept of marshalling. Marshalling is like the term that the people who deal with marshalling call serialization. Like if you have your complex data structures, how you actually turn that into a byte buffer that you can exchange in a message. And the really, really awesome thing about the marshalling that is being used by dbus is that you don't have to demarshal it to use it, right? It actually, due to O of 1 access and natural alignment in memory, all the data that comes in the message that you received from somebody is already placed so nicely into memory that you never have to copy it into anything else before using it. It's just ready-made for you. It's right at the right addresses. Everything easily accessible with O of 1 time. And there are very few data structures that are better than that. I mean, it doesn't mean, of course, a hash table, you still have to generate the hash table if you want to send that. But otherwise, it's like, yeah, there's a lot of thinking went into the marshalling. If you roll your own IPC, you will not have that. And you will spend a lot of time getting even close to the performance and the niceness of actually using this kind of marshalling. It has this feature called FD passing. You can have that on other IPC systems too. But it's really nicely integrated in dbus. It's like, especially if you do low-level system stuff, it's really, really useful thing if you can pass FDs around. FDs to devices, FD to sockets, whatever you like. You're not bound anymore to this limitation that you can only use them in the process that created them. It's very natural and very useful. There's network support. The slide actually originally said network transparency, but it's explicitly not network transparency, it's network support. Meaning that, especially in the systemd case, like if you use SDBus, like the systemd implementation of all of this, there's really nice support that you can actually connect to different hosts via dbus, and it doesn't really matter too much for the application if it's talking to a local service or to the remote service. We use it in systemd in a way that the system control command that you can use to interface with services, you can actually, like you specify -H, specify a host name, and it will go through SSH in the assumption that that's what administrators use to some other host and execute the operation there. It's really like it's a very natural extension, right? Because any operation you execute locally, you can as well execute remotely, and we hook into SSH and the key setup that you already have set up, and there's nothing new in there. Yeah, if you want to have that with your local IPC, you have to sit down and actually write a lot of code first. There's also container support that we added in the systemd context. Specifically, this means that if you have your system and you run a couple of containers that also run systemd or some init system inside of it, at least in the implementation in systemd, in SDBus, you can, with basically the same API, connect to not only remote, as I mentioned earlier, but also to any services running inside of any of your local containers. So there's the strict distinction of having local IPC and remote IPC and semi-local IPC, by which I mean the container stuff, goes away. You can connect to every one of them with the same APIs. And then this one is a really important one, bus activation. Bus activation means that services that are viable in the system don't have to run all the time on dbus. They can be activated on demand when they're needed. This is specifically awesome for system services, because I think 80% of the system services that we run on our systems are seldom used. Like if you think about a printer service, for example, I mean, how often do you actually print? You print once every week or something, and if you're a really, really heavy printer, you print twice every day, right? So there's really no need to run the print server all the time. And it goes like it's the same thing for pretty much all the other system services that we have. So it also creates a robust system, right? Like, so if you realize that, like, if something dies, and I mean, software is software, so things will crash, then it can be automatically restarted the next time some client on the local system actually wants it again. Right? So bus activation is a wonderful thing. And again, if you write your own IPC system, oh my God, you have to actually write a lot of code before you get that in place. Especially in the context of kdbus, we also put a strong emphasis on exit on idle, which is like the other side of the medal, right? Like so that your service is not only activated the first time it's needed, but also has all the functionality in place so that it can exit when it's not needed anymore. This is nothing the system will do automatically for you because it cannot know if your system service is actually idle. I mean, it can only know that on its own, like if it's still executing some transaction, if it's executing something else. But we provide race-free ways now, how you can say, okay, I don't have anything to do anymore. Please terminate connection to the bus. And then basically it's race-free because we can tell the bus to not do that if there's actually something queued so that no message is ever lost. It's actually really, really awesome. Like in systemd, for example, many of the services that we have are written in this bus activation plus exit on idle style. So that, when you boot up the system, there are only like 4 daemons running. But at any time, if you type in a command that might require another service, it will be transparently started. You don't even notice it, and goes away after a while when it's not used anymore. And that's actually how you really want to design your system. Then there's sandboxing. Sandboxing is not really available on classic dbus, but it is available on kdbus, which is really about like we want to sandbox our systems, like our apps specifically, so that the user does not have to open up all his own data to all the applications all the time. And with kdbus, you have sandboxing, meaning that your app runs with less privileges than your user would normally have. And it's not only about access control, but it's more about visibility, that the apps that you run not only get permission errors if they try to access something that they're not supposed to access, but are not even tempted to do so because they don't even see the service. So that's a really strong thing we will hopefully make use of very soon in even more stuff in the context of GNOME apps and things like that. We actually put a lot of emphasis on this because we believe that dbus should be the primary way in and out for these sandboxed apps to communicate with the rest of the system, right? Because it's really, really hard to control access in the sense of sandboxing if the IPC systems that you have don't expose any kind of information about the operations they actually really mean to execute to the kernel. Because, I mean, with kdbus, the kernel actually has a notion about method calls and these things like that, which, again, you do not have if you use the IPC primitives like sockets and things like that in a raw way. Anyway, then there's the thing, reliable multicasting. This is actually really, really an important thing. Like if you write software like a system service, and you frequently have to notify all the local clients that are interested in system changes about the fact that the system changed, right? And so you have your system service, that's the one point, and then you have 5 or 10 or whatever apps that all want to be notified when, I don't know, a network interface goes up. Traditionally, in a classic IPC system, what would happen is that you actually would have to sit down and all the clients would connect, and then if something changes, you go to every single client and let it know, oh, by the way, I changed something. Oh, by the way, I changed something. Oh, by the way, I changed something to every single one of the clients. That, of course, is pretty inefficient. So with dbus, you have this scheme of reliable multicasting. So you can actually issue one call, and it will end up at all the clients at once, which makes these things a lot more efficient. And given the way how interaction works on IPCs, it is like you really should not underestimate the importance of having this kind of reliable multicasting, because you can remove all this complexity that you have to talk to every single client. I think it's especially the way how multicasting works in dbus is a very strong point of dbus, because it's, most kind of multicasting actually works around groups, so that you subscribe to one group, and then you get notifications that are meant for that group, which basically means that the administrator, not the administrator, but the developer actually has to sit down and define that group and say, this is the group where all notifications about network interfaces coming and going go to. Or this is the group where that and that happens. dbus doesn't follow that model. In dbus, you can actually subscribe to any kind of message you like. You don't, like the developer does not have to sit down and define the groups, but you can actually have the complete freedom that you can efficiently subscribe to any kind of message you want, take precisely the message that you want, and completely orthogonally to any kind of grouping or anything. I hope that makes some sense. Then this thing is like, with dbus, you're not forced into any kind of model of operation. You know, if you look at other IPC systems, I mean, dbus is certainly not the only IPC system in the world, not even the most successful. Like if you, for example, consider that Android uses a binder IPC system, and there are probably a lot more Android devices out now than there are generic Linux devices. But the thing is that the binder kind of forces your application to be written in a certain style. The kernel interface of binder already enforces you to do threads, right? You're supposed to always keep around a couple of worker threads, and the method calls, like if you implement a service, the method calls that come in are delivered to these worker threads. So it kind of forces you to adapt this kind of binder development style, which, as I want to clarify here, is not the way how we do these things in Unix. Because in Unix, in Linux in general, like threads are usually not the first thing that we think of if we want to do asynchronous I/O and asynchronous anything. Like most of the services that we have try to avoid the complexities that threads bring. Dbus makes no restriction on how you actually want to dispatch your stuff. You could even implement it with threads, but you can also not do that and just dispatch things in a loop. So in a way, you could say, yeah, it's more like in line with the way how we develop things in Unix. Like it's more in line how our system daemons usually work. It does not force you into any kind of specific way how you have to run your stuff. Then there are global ordering guarantees, which is actually a really useful thing. Like if you have a lot of services that talk to each other, then dbus actually gives us guarantee that for every peer participating on the bus, the messages will always appear in the same order, right? It will never reorder things. It will never even reorder things between peers that don't see each other. Kind of related to this is, at least in kdbus, we can nicely timestamp messages. So we can actually derive from the timestamp, which is like a monotonic or a wall clock timestamp, when the messages have been originally created. There's also priority queuing. Priority queuing means that if you want it, you can actually ask messages to be reordered. If you, as mentioned, by default, nothing is reordered. By default, everything's you receive in precisely the order that you send it. But with priority queuing, you can step away from that if you want to. This is particularly useful for multimedia applications, because in multimedia applications, you usually have one stream of data that, like, for example, is your audio, and then another stream of data that is your control messages. And usually, it is a lot more interesting to process the control message earlier than actually to process all the audio messages that came before them, so that the reaction to key presses is immediate, and the music stream is only read when you actually need it. That's kdbus, though, there's the latter two. Anyway, this is kind of the last slide on the topic of why you want it. It's also because it's kind of standard. You know, if you think about Linux, it's the one IPC system that everything uses. Like it's on generic Linux, there's no IPC system, more applications in its systems, and system services speak. Like if you think about it, I mean, of course, the entire dbus, entire GNOME or KD desktops use it for everything they do, but it doesn't stop there. There's like systemd uses it, and before systemd, Upstart uses it as well. So it's kind of, you know, you don't have to think about that. Dbus will be available on your system anyway. If you try to avoid dbus because you think it's crazy or whatever else, you don't win anything by it because all the other software uses it. So it's kind of the standard. It doesn't mean that it's the most run IPC system on Linux, because it isn't. That is Android Binder. But on everything that's not Android that is Linux, it certainly is the standard. Oh yeah, and the last thing actually is that you have the choice. You have a couple of implementations of it. For C alone, I mean, I only put on the slides here the choices you have for C. You have 3 implementations. libdbus, which is a classical implementation. It's kind of 10 years old. It is very complete. I would say unnecessarily complex, but it does the job. There's gdbus, which is the implementation in glib. It is really good. It's very glib-ish though. So if you're not writing a glib application, it might not be your choice, but if you write one, it's the best choice. Like, it's really nicely integrated, and you feel right at home. Like, G-object is hooked up to it and things like that. And then recently we wrote in a systemd context sdbus. Sdbus was basically a look at libdbus and trying to make it much less complex. And actually, I'll give an example how dbus IPC works with sdbus, because the APIs it offers are so simple. I can show you how to write a service now in one slide, and you could certainly not do that in libdbus. So much about the advantages of why you should be using dbus. So dbus, for administrators at least, still appears to be this kind of opaque concept. They don't feel at home there. Now I want to try with basically one slide to get the concepts of dbus into your head so that you don't feel foreign, should you feel foreign to it, as much as you used to. So the concepts are really simple that dbus introduces. There are buses. Buses are basically scopes. Like, there are two buses by default. There's a user bus, or sometimes called session bus, and there is a system bus. Right? The system bus is where all the system services are, everything that's privileged. The user bus is where all the stuff that is user stuff sits around. So basically, a service that provides access to the telephone book, your personal telephone book, is on the user bus. But the service that manages the system's network configuration is on the system bus. Then you have the concept of a service. A service is basically a program that offers something on the bus. There's an object class. An object is basically an identifier. It's like, as in languages like C++ or something, it would be the pointer to the object structure, or in Java would be that reference to the object, or something like that. In dbus, it's called an object path. Sometimes they just call it object. Sometimes they just call it path. The full name is object path. It looks a lot like a Unix path. It's just the reference to one specific object that exists. There's interfaces, which do exactly what they do in Java. Java, if you ever hacked on Java or other programming languages that do OO, they know this concept of interfaces, which is just an enumeration of methods, signals, and properties. And there's member. Member here is kind of generalization of signals, properties, and methods, right? So that's pretty much all the concepts that you need to know. If you understood this, and these are not new concepts, right? Like an interface and a member is pretty much exactly the same thing as in Java as in dbus. What might be surprising is the fact that object paths are used here, because they look like Unix paths and they're references to objects, and from most programming language you're not used to being able to refer to objects not via some binary pointer, but actually via paths. But this is mostly because, like, if you do IPC systems, then you have to have a stable identifier that you actually can send across the wire that stays stable and that's clear what the other side means by that. So, if you're confused by this, then let's compare this with how you would refer to a certain resource on the web. I think everybody here knows the web pretty well. I mean, you use a web browser every day. So if you would map that, you could think, the service is basically the host name where you want to talk to. The object path is like the first component of that comes after the host name. Then the interface, the member, is basically the file that you refer to inside of some path. The interface and member, like their combination, I think you could consider it if you translate that to HTTP. And all that on a bus. Where by this I mean basically that if you're on a different network, different websites appear. Like if you, for example, in your home network, you might be able to access the router configuration page of your local router. But if you're in the Red Hat network, that's certainly not possible. But instead, you see a couple of other sites. And then in this case, I'm kind of comparing this with this here. Like depending on which bus you are, you see a different set of services. So I hope this kind of comparison makes sense. So that every time you try to think about what does this mean in dbus, you can map it back to an URL. So to give an example how this actually looks like, this is about like the method that you have to execute to turn on the screen lock on all the local sessions. So you first connect to the system bus because it's actually not per user what we want to do. We want to do it for all the local sessions regardless of the user. So you connect to the system bus. You connect to that service, it's org free desktop login, which is actually the service name. It's like in this reverse domain implementation that you might know from Java. It's a service identifier of lognd. Lognd is this little daemon that systemd has that manages things like users who log in, log out, and things like that, and active sessions and what hardware belongs to sessions and things like that. You talk to this object path /org free desktop login, which is like, this is basically the entry point object. You need to know this. Like, I mean, you cannot derive this automatically that it's this one. And you issue it on the interface org free desktop login 1 manager. And then you call that function, call log sessions. So let's explore this with, still 15 minutes, with bus control a bit. So in the context, now I need a terminal. So this is not my machine, it's Kai's, so I'm only feeling semi at home here. So in the systemd context, we introduced a set of new tools called bus control, like not a set of new tools, one new tool called bus control, which is how we recommend that people actually introspect the system, like the IPC services and things like that. It is, the concepts that bus control exposes are not new. Like glib and kdbus has one tool called that is just called kdbus, and it's very similar to this. I think this one is much simpler and much easier to use, and if you look at the command lines, they're shorter and hence easier to understand. But if you want to do the kdbus way, you can do that. You use kdbus, and it's a wonderful tool as well. So bus control has tab completion. So if you call it without any arguments, you see this. I hope the font is actually. You want to. Shit. Okay, it's not as pretty if the font size is so big because you only see 4 of the columns. But basically, here you have the service name. In this case, these are numeric ones. They're automatically assigned to you. It's basically, if we scroll down, you see these other ones. These are the ones that look like Java, like the service names. And like the one that I showed earlier, org free desktop login 1, is among them. The distinction between these up here and these down here is basically the same one as on classic internet between an IP address and a DNS name, right? This is the, this is the IP address basically that's automatically assigned, and then you can also have a nice name to it. The nice name is how people recognize you. That's really the same reason why if you type into your web browser www.microsoft.com, it's easy and nice and everything's clear. But typing in the IP address of the Microsoft web service would not be much fun. Actually, this space is hugely redundant if you look closer, because if you like org free desktop login has both this well-known name and this unique name here. And if we scroll to the right, we actually see that the numeric name of it. Anyway, so this is like the first thing that you can do. You see all the system servers that you have. You see the PIDs that are registering the system service. You see the processes, like the names. You see which users do that. Then the unique IDs, then the units, sessions, description, and things like that. It's already really, really useful. But what I actually wanted to show, how you can actually introspect system services easily. So what do? You type in bus control introspect. It's kind of obvious. And then you type tab. And it will show you the list again that we saw earlier of all the servers that you have. Let's stay with that example that I showed earlier with the lock screen. So we do tab completion, and let's have a look at org free desktop login. Now we press tab again, and it shows me all the objects that exposes. As we saw earlier, like basically you have objects here. You have an object for each physical seat on the machine. You have an object for each user that's logged in each of the user sessions. In this case, as well as an entry point object. The entry point object in this case is a /org. Sorry, I should not repeat myself. I already typed that anyway. So, okay, now the tab completion is confused. Oh, no, it's actually not confused. Anyway, if we do this, right, like we said, the service, and this is the object path, then it will show us this. This is basically what this object exposes. So you see here, this is an interface name, and exposes one method called introspect. This is another interface name, dbus peer, and 2 of methods. And this one is a third one with 3 methods and 1 signal. And then Like basically these upper interfaces are completely generic interfaces. Every object on dbus exposes at least 2 of these 3. And then you finally see here like the interesting interface in this case is org-free desktop login manager. And if we scroll down, we wanted to issue the one that's called log sessions. Yeah, it's this one. And you see it's a method. You know, there's a very similar call actually called log session in singular, and that only logs 1 session, and it basically, you know, this column is basically the parameters. It's in a very short way to express what the parameters are. S means a single string, a dash means nothing, right? And a B means a Boolean, and a UPP means an unsigned, and a Boolean, and things like that. It's actually, like, if you realize it once, it's kind of obvious what it means. Yeah, and it also tells you what it returns, like in this column. Anyway, let's now call one of those methods, because it's easy. How do we do that? We use the same command line, but instead of doing introspect, we do call. Then we press tab again. Now it makes a suggestion of which interface to call. So we say it was that login interface, login1 manager. We press tab again, and it says, yeah, which one of the methods do you actually want to call? And we wanted to call the one that's called log sessions. I do not have your password. So this will fail now because of authentication, actually. I mean, I talked about this earlier, that IPC requires authentication, of course. In this case, this runs as the user Kai, who's unprivileged on the machine. He should not be able to lock all the sessions of all the users on it, because, I mean, then you can play games with the other people working on this machine. So if we issue that, it will say access denied. And, OK, I'm out of time, apparently. Anyway, so this goes on like this. So let's just... shit, that's F5. One last slide. This is basically, if you do that in C, it's just this, right? You connect to a bus with SDBus Open System. You issue one method call, and that's it. Yeah, it's that simple. And I can even show you the next slide. This is a service, you know? This was just calling a message. This is a service. It's a stupid service that just implements a stupid calculator that can add. So what does it do? It opens a system connection. This was without any error checking, so you shouldn't deploy just like that. You say, I want an object here. You specify the vtable, which is defined in the structure, which has one method called add. It takes an unsigned, like an uint32. Uint32 is returned. This function is called. It's defined here. What does it do? It reads the 2 parameters. It checks if that's an overflow, returns an error, which is returned back to the application. Otherwise, it returns a sum. Yeah, this is a complete service. It's not any more complex like that. And this is the kind of the reason why we put SDBus together, because I can now put this on one slide and tell you how to write a dbus service. And it's not any more complex than that. Anyway, I'm out of time. That was actually already my last slide here. So because I'm out of time, I probably can't take too many questions. If you have questions, though, fetch me outside. And actually, I think I still have 2 minutes, right? I think I have
you
1
have
minute.
1 minute.
So, OK, because I have 1 minute, we can still take one question. There's a question up there. Journal deremoting, like, you know, while this has network support, it doesn't mean like if you actually want to write something that focuses on networking, it's not the right choice. This is for local IPC, and then you can extend it to use it on the network. But if your central focus is doing some network stuff, then it's, I mean, this is no replacement for HTTP. Like if you want to design a protocol that is really just about communicating over the network, then you probably should consider HTTP more than this. This is really about local programs talking to each other, and then having a nice extension that they can also talk to other things remotely. But the focus is clearly on local. Well, as good or bad as you would update running systems with anything else, right? I mean, for dbus generally, if you define a vtable, if you method calls and things like that, it's API. Like you have to provide API stability. You have to you cannot change the method calls randomly if you want to. You have to stick to them and support them for a longer time. It's much easier though to keep stability of a bus interface than it is, for example, in keeping stability than a C library. Because a C library, if you break something, it has horrible results because all the programs start crashing if you don't do that carefully. Dbus is a much softer thing to break because there's always error checking in everything that's done over the bus, because it potentially is in a different privilege level on the other side, so you can never trust the other side to send you crazy data, so you actually need to always verify what you get, and you cannot just, if you follow what I mean. So basically, yeah, I think I mean, this is not an answer, like, I mean, generally, runtime updates of running systems are a really difficult thing anyway, like, because if things talk to each other, you have to update them all at the same time. I think the proper answer for all these questions about runtime updates is not doing them, and going for something that does atomic offline updates, like Atomic does, or something. Okay, we're out of time. Thank you very much. If you have further questions, I'll be outside.